Hi folks, it's Mr. Moodledge here with another video, and in this lesson we're going to take the trig graphing skills that the trig graph skills from the last lesson and apply them to real life situations here. So in today's lesson, the examples that we're looking at include a windmill, daylight hours, tides, a Ferris wheel, and a spring. So even though those situations sound very different, the math structure is the same, and each one is periodic, meaning it repeats in a cycle. Okay, so for these problems, we're usually building a function like y equals a sine k t minus h plus d, or y equals a cos k t minus h plus d, where the variable t right here represents time. Okay, and here's the strategy that we're going to use every time. We're going to figure out the middle value, the equation of the axis, which becomes d. We'll find the amplitude, which becomes a. For the period, we calculate k, and then we decide whether a sine or cosine makes the most sense based on the starting position. Right? So sine or cosine based on the starting position. Okay, so let's just jump right in and look at this first problem that we have here. So this one we solved in class, so let's just take a look at it again together. It's a windmill problem. So problem 1 says a small windmill has its center 6 meters above the ground and blades 2 meters in length. In a steady wind, a point P at the tip of one blade makes a complete rotation in 12 seconds. Right? And we want, so ideally for A, we want a function that gives, we want to find out the function that gives the height of point P above the ground at time t. So let's pull out the important information here, right? The center of the windmill is 6 meters above the ground. That's what it says right here. And this is the middle height. So if we think about the ground here, 6 meters above the ground is the middle. So that's the midline or the equation of the axis. So d is equal to 6. So h, that's not the horizontal, that's not the phase shift. That is the d value, right? The height. So very good. That's what I've labeled here, the midline. Okay, the blade length, so I can write that down here actually. D is equal to 6. Okay, put a box around that. The blade length is 2 meters, and this means that the point goes 2 meters above and below the center. So A is equal to 2. Okay. Next thing we know is that the windmill makes one full rotation every 12 seconds, so the period is 12. So period is 12 seconds, which I've labeled right here. And from this, we can actually calculate k. It says period is equal to 360 degrees divided by k. So k is equal to period 360 degrees divided by period. So k is equal to 30. Okay. All right. Very good. Okay, so now what we want to do is think about the starting point. So at t equals 0, and I've graphed it here, even though it's not asking us to draw a graph, it's a good idea to just draw a sketch because we can see clearly what's going on here. So at t equals 0, we can see that the point starts at the highest possible point. So a cosine curve starts at the maximum as well. So cosine is probably the best choice and the easiest choice to model this this equation, this curve by, this function as. So therefore, we can say if it's a cosine, then well, the h value or the phase shift is going to be 0. not the height, but the phase shift. So therefore, we can use this information and say that our function, h of t, is going to equal, well, 2 cosine, k is 30, there is no phase shift, so t, and plus d. So that is our function. Okay. Oh, and sorry, my d here is 6. Yes, there we go. Okay, nice. So for part B, that's part A. All right, check. For part B, we are asked to calculate the height at 5 seconds and at 40 seconds, right, as per question. So for 5 seconds, all we're doing is replacing t with 5 here. So as we've done here, I'm calculating 30 times 5, 150, so cos of 150 times 2, and then adding 6 to that. And if you do the math in your calculator, you'll get 4.3 meters. Okay, so that's good, approximately. And then likewise for 40 meters, we're replacing t with 40 here. So 30 times 40, and then cosine of that number, so cosine of 1,200 times 2 and then plus 6. This is going to give us an exact value of 5 meters. Okay, so that's how we figured that out. So that the height after 40 seconds is 5 meters, and the height after 5 seconds is 4.3 meters. Okay, so now for part C, we're trying to, it's asking us, when is point P exactly 7 meters above the ground? Right? So we set the function equal to 7 this time. So the h of t is equal to 7, and we are solving for t. Right? So what we want to do is subtract 6 first, which we've done here, right? Minus 6 here, both sides. And then we want to divide by 2. So divide by 2 both sides to get to this right here. And now I'm trying to figure out, when does cosine equal a half? To make this easier, I make this change of variable just to make my life a little bit easier. I should just say temporarily, let theta equal 30t. So what value of theta makes cosine equal to half? Well, this is where I can draw my little, grid here, sketch, and then I can be like, well, when is cosine positive, first of all? Well, it's going to be CAST, so in the first and fourth quadrants. So then I'll draw my two terminal lines there, terminal arms, and cosine half, meaning, well, the adjacent has to be 1, and the hypotenuse has to be 2, and that means the opposite is root 3. So this is our special triangle. This is the 60, 30, 90 triangle. So this has to be 60. Likewise, this is 60. And so my principal angles are 60 and 300 degrees, right? Around, take away 60 from 360 and you get 300. So this is theta 1 and theta 2. That's not our answer, because remember, we made that shift. So now you can replace theta with 30t again. So 30t is equal to 60. Here 30t is equal to 300. Now you can solve for t. So t is equal to 2 seconds, and then t is equal to 10 seconds here. So during the first rotation, so we could see right here, during the very first rotation, as you're going down, the point is 7 meters above the ground at t equals 2. And still during the first rotation, it's going down, it's coming back up again. The point P is exactly at 7 meters at 10 seconds. But if we wanted all possible times, we could add a period of 12 seconds to this answer to get something like this. So t is equal to 2 plus 12n. And then here t is equal to 10 plus 12n. And where n is a whole number. N is a whole number. And so this would give us all the possible times for when the height is exactly 7 meters. Okay, but here we're just doing it for the first cycle for the first rotation. So that's enough. Okay, that's it for problem. That's it for problem 1. Now we can move on to the next one. So for problem 2, this is dealing with daylight hours. Let's read the problem. So it says here, a city averages 14 hours of daylight in June, 10 hours in December, and 12 hours in both March and September. Assume that the number of hours of daylight varies sinusoidally over a period of 1 year. So for part A, write an expression for h, the number of hours of daylight, as a cosine function of t. Let t be in months and t equals 0 correspond to January. Okay. And what is the average amount? And for B, what is the average amount of daylight hours in August? Okay. So we need to write a cosine curve for A. We need to write a cosine function for h, which is the number of daylight hours as a function of t, where t is months and t0 corresponds to January. Okay. So let's identify the max and the min here. Okay. So let's just see here, just to help us like graph this. It's always a good idea to draw a sketch. So let me, again, it's not asked of us, but it's good practice. So let me just draw our sketch here. This is going to be time in months, right? And then this is going to be hours of daylight in hours. Okay. So here I have, let me label the months, right? We start at time 0, that's January. And then I have February, March. Maybe I'll label this way. And it's interesting I'm doing it this way because I know the period is 1 year. There's 12 months in a year. I'm breaking up into quarters strategically, right? Because that's when my function has those key points of like, the key instances like neutral or midline, max, neutral, minimum, and so on. So every 3 months something's happening. But so January, February, March, April, May, June. So wait, hold on. 1, 2. I should put it here. January, February, March, April, May, June, July, August, September, October, November, December. So I'll put December here. So wait, let's just count this again one more time. So there are 12 months. So there's 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. Okay, all right. Here's what we're going to do. It's okay. I will just mark this. I don't need to, again, I don't need to overcomplicate this. Let me just mark it normally. January, February, March, April, May, June, July, August, September, October, November, December. Okay, so I just marked it normally like normal months. I don't need to overcomplicate it and split it into quarters there. Okay, so here let's identify like here, well, the hours in terms of hours, the minimum is 10, and then it looks like I have 12 hours here, and then the maximum is 14, right? Those are the information. That's average 14 hours of daylight in June. So March, April, May, June. So I could put a dot at 14 here for June, right there. All right, that's June. And 10 hours in December and 12 hours in both March and September. So 10 hours in December. So over here, that's 10 hours. And then I have 12 hours in March and September. January, March, 12 hours in March, and 12 hours in September as well. Okay, so if you want to connect, if you want to put the midline, well, how do we know this is the midline? We're actually going to calculate this, but let's just put these dots here for now, just so we could, these lines rather, so we can connect these a little bit easier. Okay, so it looks like this. My graph as a a rough sketch looks like this. So max to min, back to minimum, back to neutral, and to minimum. Okay, so that's like not a full cycle, but we could see the key quarters there and when they're happening, right? So like that. Yeah. So every 3 months, which is a quarter of 12, something is something is happening. Okay. So like it's going from a minimum to a neutral line or neutral to max and so on, vice versa. Okay. So this is good. We have our sketch here. This is h is equal to 12 hours. Okay, so let's actually imagine like we didn't graph this or for whatever reason we're trying to figure it out. Let's identify, well, the maximum and minimum, right? So this is a max. Max is equal to 14. That's the largest amount of daylight hours, and the minimum is equal to 10, right? So we can actually figure it out, which we did here. So this is min. We did here, but the midline here, D, is equal to 14 plus 10 divided by 2, max plus min divided by 2, which is actually 12. Okay, and I could put a box around that. And that makes sense because, March and September both have 12 hours, which is the middle value. Now we can look at the amplitude. So A is equal to 14 minus 10 divided by 2. So 4 divided by 2 is 2. Okay. And that also makes sense because here to here is 2 and here to here is 2. That gap, right? I know that 1 full year is 1 year, which is 12 months. So K is equal to 360 divided by period. Okay, please make sure to write that properly. It's not period divided by 360. It's always 360 divided by period is K. And so this is 360 divided by 12, which is going to be 30. Okay, so my K is 30. And now we just need to be careful with the numbering, right? So this is actually equal to T equals 0. February is T equals 1, T equals 2, T equals 3, dot, dot, dot. 4, 5, 6, 7, 8, 9, 10. Yeah, 10, 11. That's kind of how the numbering system works there. Just be careful with that. And so the maximum happens at June, which is at T equals 5 here. That's the maximum. And I want to notice here, so now that I've sketched this graph, it's easier for me to answer these questions, right? So I want to, it starts at a maximum, and I want to model it as a cosine function of t. So I need to look at that maximum. So it's starting at 5. So therefore, my horizontal shift, h is equal to 5, my phase shift. So I can then say that for a, cosine, so I'm going to make this a cosine function. So I'm going to say h of t, the hours of daylight in terms of the time of the year, the month, is equal to a, which is 2, cosine. My k value is 30. I'm going to have t minus 5, phase shift to 5 units to the right. So then it starts actually, instead of here, it starts here at the top. It shifted 5 months over. Sorry, 6 months over for June, right? And plus 12. And that's all. So that's my function modeled as a cosine. So for part B, I'm asked what is the average amount of daylight hours in August? Well, in August, I can see that my time value is 7. So t is equal to 7. So all I'm going to do here is just calculate h of 7. Right? That's what it's asking me for. So 2 cosine 30 and then I have 7 minus 5 plus 12. So at the end of the day, this is going to be 2 cosine 30 times 2. This is going to equal 2 cosine 60 plus 12. Cosine 60 is actually a half. So this is going to, again, you could use a calculator here. So this is going to be 2 times a half plus 12. So this is going to be just 13. So the average amount of daylight in August is going to be 13 hours. Okay. So the big takeaway here is for these daylight problems, the midline right here is the average daylight, and the amplitude is like that seasonal variation, and the period is 12 months, right? So we could see that there, 12 right here. Well, yeah, 12 months, because from January to December. Okay, nice. Cool. Let's see here. All right, cool. So let's move on to example 3. Taking a look right here. Okay, good. So in example 3, we're looking at a tides question. And yeah, so this is all about tides. So let's read the problem. A group of NHS students decided to study the sinusoidal nature of tides. Values for the depth of the water level were recorded at various times. At t equals 2 hours, low tide was recorded at a depth of 1.8 meters. And at t equals 8 hours, high tide was recorded at a depth of 3.6 meters. Right. So it's asking us in this question to sketch the graph of the function, and then write the equation of distance in terms of time. And we're also asked for part B, what is the depth of the water at t equals 21 hours? Okay, so let's, we need to sketch it. So let's actually make a grid here. So we have rough grid. So there's my y value. There's my x. So this is going to be time. I hope you realize now for these problems, most likely our x-axis is going to be time, right? So here in hours, sometimes it's in months, depends on the problem, right? And then in the y, it's going to be, in this case, since we're dealing with tides, it's going to be depth. And that's in meters. Okay, so at t equals 2, so maybe I'll go like 0, 1, 2. A low tide was recorded at a depth of 1.8 meters. So that's just going to be, let's say that's 1.8 there. Okay, so low tide. At t equals 8 hours, a high tide was recorded at a depth of 3.6. So 2, 3, 4, 5, 6. So 2, 3, 4, 5, 6, 7, 8. I'll go 9, 10. So that's at 8 meters, right? At 8 hours right there. I'm at a high tide, 3.6 meters. 3.6. So at 8 meters right there. Put a dot right there. Okay. So very good. So put a dot right there. At 2 over there. So now, that's low tide and high tide. Before connecting these dots, let me figure out some important things. So that's pretty much what I'm given. I've made use of this, and I've made use of this. Let's now calculate some things. So let's figure out our midline here. So our equation of the axis, this is going to be d. So I'll do that right here. D is equal to max plus min divided by 2. So max is 3.6 plus minimum is 1.8 divided by 2. And that's actually going to be exact. Well, it's going to give us 2.7 if you type this in the calculator, right? So now I know this middle is going to be 2.7. Put a dotted line here. And in fact, I can also predict when that's going to happen. It's going to because this is like half a period, right? From minimum to maximum, that's like half the period. So at halfway between there, right? If this is a half of that is going to be, so that's going to be 2 plus 6, which is 10 divided by 2. So 2, 3, 4, 5. At 5, I'm going to reach that point right there, right? That's how we could figure that out. Just, it's good skill to know that. Just good piece of knowledge. Okay, so the amplitude is going to be, so we got D. The amplitude is going to be 3.6 minus 1.8 divided by 2. So this is going to be 1.8 divided by 2, so 0.9. Again, this distance right here, you can see it's also 0.9. And now you're at a point where you can actually like connect the curve here. You can kind of like this, right? And that's for that's half a period right there. Okay. So let's go ahead here and calculate our K value. So the period here, and this is again one of those instances where we mentioned it, period. So this is half a period. Half of P is equal to 2 to 8, which is 6 hours. So then a full period, double both sides, you get 12 hours. So that's my period, P. Okay. So the full period is 12 hours. And now I can calculate my K value. So K is equal to 360 divided by period, which is 360 divided by 12, which is going to be 30. Okay. So I got my K value, and now we need the equation. I could see here at T equals 2, I'm at a minimum. Doesn't really tell me what kind of function I need to model this as. I'm going to model this as a negative cosine because I know a regular cosine starts at a maximum. So I'll just model it as a negative cosine. So I'm just going to say the depth in terms of time. So let's just say that is D with respect to T. So, if I model it as a regular cosine, by the way, my horizontal phase shift is going to be 2. So we'll see how this is applied here. So this way, depth as a function of time is going to equal a negative cosine. So the amplitude is 0.9 cosine. Why is it negative? Because it's starting at a minimum, not a maximum. And then I know my K value is 30. So I'm going to have T minus theta, or T minus X, and my or T minus H, I should say. And my H value is 2. So it's going to be T minus 2 here. And then I'm adding my equation, the axis, vertical shift of 0.9 there. Or sorry, 2.7 rather. 2.7. Okay, so that is my curve right there. Equation of the function right there. Okay, so, and we can obviously, like when you're given a question like that, when you calculate a model, when you get a model equation like this, you can always check, right? You can plug in values of 2 here for T and verify that it is in fact 1.8. Cosine of 0 is going to be 1, so 2.7 minus 0.9 is in fact 1.8, and vice versa. You could check at 8 as well. So those are good ways to check, and so that would give like high tide, for example, and it would work out, right? So for part B, so we're done with A. For part B, at what is the depth of the water at T equals 21 hours? Well, now you have the time. So for part B, this was for part A, by the way. For part B, you're finding the depth at T equals 21 hours. So D21 is equal to negative 0.9 cosine of 30, and it's going to be 21 minus 2, 21 minus 2 plus 2.7. Okay, and so, that's a 7 right there, sorry. Yeah, there we go. And if you plug this in the calculator, you're going to get, let's do it right here. So negative 0.9 cosine 30, 21 minus 2 plus 2.7, and you'll get, okay, let's see if we're doing this good. Yes, I need to make sure to put the brackets here. Otherwise it doesn't know. Yes, okay. Make sure when you're doing this, folks, make sure, like, this is a common mistake that it's possible to see. Make sure to put brackets here, like another set of brackets, because if you don't, it's going to calculate cosine of 30 and then multiply that by 21 minus 2. Like, that's not what we want. We want it to know that I want you to find the cosine of 30 times 21 minus 2, right? Like that. So it's very important to put that bracket right there, right here and here, right? Because that's what the function is supposed to look like, right? It's supposed to, like, we don't really explicitly do it, but it's like that, right? So it's a good thing to note there. So yeah, if you type it exactly like that, then you'll, with the brackets, you'll get a value of t, which is, or sorry, the depth, which is d is equal to approximately 3.5 meters. Okay, so the water depth at 21 hours is approximately 3.5 meters. And the key takeaway here is for tide problems, remember high tide and low tide gives you the max and min respectively. And the time from low to high tide is half the period. All right, that is half the period right there, half of P. Okay, let's move on. So here we are looking at a Ferris wheel problem. So problem 4 says we have a Ferris wheel with a radius of 9.5 meters, rotates once every 10 seconds. The bottom of the wheel is 1.2 meters above the ground. Find the equation of the sine function that gives the rider's height above the ground in meters as a function of time in seconds, with the rider starting at the bottom of the wheel. Okay, so let's just annotate or sketch here a little bit. This is the ground, let's say, right? And then 1.2 meters above the ground is where we like actually the bottom of the Ferris wheel. That's where like the bottom is. But we know that, the Ferris wheel has a radius of 9.5. So from this middle here, to the bottom of the Ferris wheel, that radius is equal to 9.5 meters. And I know that it's actually just like spinning this way, right? So it's just going around. That's what Ferris wheels do. All right, cool. All right, so let's just draw a sketch here to help me picture what's going on. So here, sketches are always nice. So here I have, this is going to be time in seconds, because that's what the unit of time is in this question. And then this is height in meters. Height in meters. Okay, so I have here rotates once every 10 seconds. So if this is t equals 0, then one full period later is going to be 10 seconds. I can go ahead and actually split this into quarters. So half of 10 is 5, half of 5 is 2.5, and then here half of 5 and 10 is, or the middle is going to be 7.5. This is just a good skill to do because it'll make life a little bit easier, because I can identify really easily these key features, right, of my graph. So the rider starts at the bottom of the wheel, and at the bottom, the location of that rider is just 1.2 meters above the ground, right? That's literally their height. They're at the very bottom. So my minimum is going to be 1.2 meters. And what I want you to know is that we can actually calculate this here. Well, let's actually go into this. D is actually going to be equal to, so actually, wait 1 second. Before we go into this, let's actually figure out the most logical thing here, which is the amplitude. Here, we're actually given the amplitude. really nice and easily. That is the radius of my Ferris wheel. So amplitude is 9.5. Okay, so I put a box around that. The bottom of the wheel, since it's 1.2 meters, right, above the ground, the center of the wheel, the middle, is going to be 1.2 plus 9 plus a radius. So the center of the wheel, the equation of the axis, is 1 radius above the bottom. Well, the bottom distance, like the bottom of the Ferris wheel, plus 1 radius. So that's just going to be my d value here. You can see it intuitively. It's going to be 1.2 from this picture plus 9.5. So that's going to be 10.7. Okay, so it's my d value. So I can actually mark that here, 10.7. And then you can also see now, if you add the amplitude 9.5 to that, you'll get the maximum, which is 10.7 plus 9.5, which is 20.2. 20.2 meters. Okay, so now you have all these key pieces of information. You can actually start to plot them, right? Or to make this graph. So the rider starts at the bottom of the wheel. Then to like a quarter period, they have to go up here to the midline. Then at another quarter, they have to be at the maximum. Another quarter, they have to be back at the middle. At the end, they have to be back at the bottom. So that's what my graph looks like. Right? When you really draw a picture, it becomes easier all of a sudden, because now it becomes like the previous lesson, trying to figure out the equation of this. Okay, good. So I know my midline, I know my amplitude. So the period here, P, you can see here, well, that's given in the question. P is equal to 10. So P is equal to 10 seconds. So that means K is equal to 360 divided by 10, which is 36. Okay, so my K value is 36. The rider starts at the bottom. So when they start at the bottom, this is a very natural negative cosine, right? Starting at the bottom. So that would mean that, like if I made my phase shift equal to 0, which is true for a negative cosine, then using all this information, I could say that the height of the rider with respect to time is equal to a negative cosine with an amplitude of 9.5. And I'll put brackets here just to make it easier. So the K value is 36. And then I got my T with no displacement here. So I don't know horizontal displacement, plus 10.7. Okay, so that is going to be the equation that works perfectly, that fits this model perfectly. Okay, right there. All right, very good. Oh, one thing though, I just realized this question is asking for a sine function. Okay, so this would be the natural cosine function, which works perfectly. So let's convert it into a sine form. So a sine curve normally starts at the middle right here, and then it goes up. And if it starts at the bottom, we shift it over, shift it right by a quarter of the period. So by 2.5. So essentially, this is for cosine. For cosine, h is equal to 0. For sine, h is going to be, when it starts in the middle, goes up 2.5. For sine. Specifically, this is for a negative cosine, right? This is for a positive sine. So therefore, with that phase shift, I can say h of t is equal to positive 9.5 sine 36. And then I can have my phase shift here, t minus h, and h is 2.5. T minus 2.5, and it's going to be plus 10.7. Everything else stays the same. It's just that phase shift. So that's another equivalent way, to give the equation for this function. As requested, it's for a sine. So we can always check this by plugging in, let's say, t equals 0. If you do the math at t equals 0, you'd get like here, it'd be a negative 90. And we know that sine of negative 90 would be negative 1. And then that would make this, negative 9.5 plus 10.7, which is 1.2. And we know at the time at 0 is 1.2 meters. Or sorry, the height at 2 meters is, the height when the time is 0 is 1.2 meters. So yes, the rudder starts at the bottom. And we can also check with, if at 5 seconds they're at the top, and it would work out as well. So our sine equation works. All right. Good. All right. We are at the last problem here. So for this one, a mass is suspended from a spring. So the mass suspended from a spring is pulled down a distance. So right here, mass suspended from a spring pulled down a distance of 2 feet from its rest position. The mass is released at time equals 0 and allowed to oscillate. Okay, so this one's an interesting one. If the mass returns to its position after 1 second, find the equation that describes its motion. This is like the period. What is the distance from rest position at 0.2 seconds? And then at what times is the height of the spring 0.9 feet above the rest position? Okay, so we have 3 different types of sub-problems here, which is what makes this a good problem. Okay, so let's draw a sketch here of our graph just to visualize it better. So here on the x-axis, I have time in seconds because the units of time are in seconds. Okay, and in the vertical here for the y-axis, I'm going to have distance, and distance in feet, FT. Okay, so let's see. I could see here, so part A asks for an equation that describes its motion if the mass returns to its position after 1 second. So 1 second. Here, I'm measuring distance from the rest position, right? So the rest position, I want to make like the midline. So that's like d equals 0. So d is going to be 0 meters. That's my midline. The amplitude, so I start 2 feet from the rest position. I let go. So the amplitude is actually equal to 2 meters, or 2. Right? So what's going to happen is my minimum is going to be at -2, and my maximum is going to be at +2. So really, I should probably make this graph like this. There we go. Center it a little bit so it's easier to see. So that's going to be at -2, +2 here, and at -2. And 0 is going to be like the rest position, the midline. Okay, so I could see I start at -2, right? Pulled down, and if it's released at time 0. Okay, and then at 1 second, so literally 1 second is the period. It comes down to -2 again, its original position. So I'm going to split 1 second into quarters here. So half of 1 second is 0.5. Half of each of these are, like, these quarters here are 0.25, 0.75. So this makes it easier. So now I can kind of picture this graph. It's going to go from minimum to midline, midline to max, max to midline, and then midline back to minimum. So I kind of have my shape of my graph. It looks like this. Okay, good. Very nice. So now I can easily come up with the equation here. What else do I have here? Oh, the period is 1 second, right? P is equal to 1s. So using this, I can find k, because k is 360 divided by p, or divided by 1 in this case. So it's just 360. Okay, so k is 360. Essentially, this graph has been like compressed by 360. Hence these numbers, right? Instead of 0, instead of 0, 90, 180, 270, 360, it's essentially like squished 360 times, compressed by that factor. So the period is 1. instead of 360, right? Okay, so we've modeled it here. Nice. So clearly you could see that this is like the most natural one to model this as is as negative cosine. So if we say that my phase shift is 0, then I can model this curve as a negative cosine, this function. So I'd say that you know, distance as a function of time is equal to negative cosine with an amplitude of 2 cosine, and the k value is 360, and then t, and my equation of the axis is 0, so I don't need to add that, and that's it, plus 0. So that's my function for part A. Okay, for part B, that's it right here. For part B, what is the distance from rest position at 0.2 seconds? So this is always nice. I'm just plugging in 0.2 for t and figuring out what does it evaluate to. So cosine 360 times 0.2. So if I plug this in here in the calculator, I'm going to get negative 2 cos. Whenever you're dealing with trig functions, like it's always a good idea to put brackets, right? So cos of 360 times 0.2. If you just do cos, if you in your calculator, if you just do cos 360 times 0.2, your calculator will calculate the cosine of 360 and then multiply that answer by 0.2. That's not the same as the input is 360 times 0.2 in the cosine, right? So just be careful about that. And if I do this now, I'll get negative 0.6 to 1 decimal place. So that is the distance. So at 0.2 seconds, I'll be like negative 0.6, like over here, because it's 0.25. I'm here at 0, so 0.2 would be like somewhere right over here, would be in the negative. That makes sense. Okay. All right. So that's in feet, by the way. Okay. And then last question here is, or last sub question here is, at what times is the height of the spring 0.9 feet above rest position? So let's actually picture this here for a second. So 0.9 is going to be roughly here, right? 0.9. So you could see it should actually be at that height at 2 times here and here. So we're trying to figure out what is this t and what is this t. So let's call it T1 and T2. Trying to figure out those 2 times. There's 2 answers here, right? Given for that y value, or given that distance. So very good. Good. And just to recap here, in this question right here, the negative tells us that it's below the rest position. That's all it is. So 0.6 feet below the rest position. So for part C, since the height of the spring is 0.9 feet above rest position, means positive 0.9. So we set the d of t equal to 0.9. So 0.9 is equal to negative 2 cos 360 t. Okay, so I'm going to divide both sides by negative 2. So I get negative 0.45 is equal to cosine of 360 t. All right. And so now I'm just going to, for the sake of, like we did this in a previous problem, I'm going to let theta equal 360t, just so it's easy. So I get something like this now. I get cos of theta is equal to negative 0.45. So now I'm just trying to figure out what theta is. If you think about this, theta is negative, so C-A-S-T. Theta is negative in quadrants 2 and 3. So here and here, right? This is not a special triangle, right? So it's okay, we have a calculator. So the inverse cosine, so cos inverse, so theta is going to equal cos inverse of negative. Okay, so here's what's interesting. Well, yeah, you can literally take the cos inverse of 0.45, negative 0.45, and see what we get here. So cos inverse of negative 0.45. We get theta 1 here. So theta 1 is equal to 116.7 degrees. Okay, so this is this angle right here. Theta 1 is equal to 116.7 degrees. You can see here, if that's theta 1, then um, this angle right here, this related acute angle, would have to be 180 degrees minus theta 1, which is 180 minus answer, so 63.3 degrees. And then you can see this is also 60. It's the same related acute angle, 63.3 degrees. So if I added to 180, I would get my theta 2. So theta 2, this angle right here, is going to be 180 plus that related acute angle, right, for quadrant 3. So this right here, theta 2, is going to equal my 180 degrees plus the related acute angle, so 63.3 degrees. So that's going to be 180. So the answer plus 180. So 243.3. 243.3 degrees. Very good. All right, nice. Very good. Yeah, all right, that's good. That makes sense. Very good. So now we can actually solve for t, right? For what matters. So remember here, not theta 1, but theta was 360t. So we could say 360t is equal to 116.7. Divide both sides by 360. So 116.7 divided by 360. We get t1 is equal to 0.32 seconds. And then here we get 360t, because that's what theta 2 is, or theta is. 360t is equal to 243.3. Divide both sides by 360, so 243.3 divided by 360 gives us t2 is equal to, or another time, I'm just calling it t2, 0.68 seconds. Okay, so here we have our two time values. These are the two answers. So the spring is 0.9 feet above the rest position. So 0.9 feet above the rest position at T1 is equal to 0.32 seconds, which we figured out right here, 0.32, which makes sense, a little bit above that time. And then here, T2 is, the second time it occurs is at 0.68. This is why sketch is helpful, because we could see like a quick judgment check, it does make sense. It's less than 0.75 as per this graph. Okay, within the first cycle, right? This is all for the first cycle, so we just leave our answers as such. All right, so a final summary here, just to conclude. I know this video is a little bit long, but you can skip and kind of watch what you need to. Every application problem today followed the same pattern. First, we identified the midline, or equation of axis. In real world problems, that's usually the average value or the center position here. Next, we identified the amplitude. That's the distance from the middle to the maximum or minimum, right? Third, we identified the period. So that's how long one full cycle takes. And from that period, we calculated the k value using 360 divided by the period. Finally, we chose sine or cosine based on the starting position, right? Or the requirement of the question. If the object starts at a maximum, like here, we used a positive cosine, such. If it starts at a minimum, like here, like over here, we used a negative cosine. If it starts on the midline going up, sine may like honestly, sine's easier, right? As we did here. But I guess here it needed to be as a cosine. So here's a better example of sine. Yeah, so it starts at a midline, or if we want it to start at a midline, we shift it, and then it would be and going up, it's a sine. So always remember to include units, and then think about whether your answer makes sense in the real world situation. All right. So that is all for this lesson, folks. Here's your homework from the Nelson Functions 11 textbook. There's 2 pages right there. So go ahead and give that a try. Thank you and have a great day.